Hello everyone. Today I would like to discuss the concept of naive Bayesian classification with the help of a worked example. The naive Bayesian classification technique is based on Bayes' theorem and has been found to be an effective classification methods for many applications, including spam email filtering. So, naive Bayesian classification is thought to be a simple but powerful technique. So, it is based on the Bayes' theorem with the assumption of class conditional independence. Now, Bayes' theorem is based on the concept of conditional probability. Now, you must already know that probability is a way to approximate randomness in nature. So, if there were an event A, then probability for the event A to be true is termed as simple probability. So if we consider the concept of probabilities, probability is the chance for a given event to be true. And there are mainly three kinds of probabilities. Simple, joint, and conditional probabilities. If there were an event A, then probability for an event A to become true is represented by P of A, and it ranges anywhere between 0 and 1. If there were two events, when we come to joint probability, if there were two events A and B, the probability for both events A and B to be true is termed as joint probability. Whereas if A and B were events again, conditional probability is read as P of A given B. This is the probability for a given event A to be true, provided we already know the event B to be true. So this conditional probability forms the basis for Bayes' theorem, and Bayes' theorem with the assumption of class conditional independence is the main driving force of naive Bayesian classification technique. So if we loosely look at the meaning of class conditional independence, sometimes people even term it as just conditional independence. It assumes that a particular feature is independent of any other feature for a given class, in a given class. So if there are several class labels, for a given class label, the presence of one feature is independent of the other. Suppose we have a data set studying the effects of COVID. Suppose that there were a feature fever which influences the outcome COVID. Now COVID is your class which takes on two labels, presence or absence of COVID. So if the presence or absence of fever would trigger the presence or absence of COVID, then the feature fever is dependent on the class. Suppose there is yet another feature breathing difficulty which also influences the class, then class conditional independence says that for a given class label, it could be yes or no, the values of the feature fever would be independent of the values that the feature breathing difficulty takes. This assumption tends to simplify the Bayes theorem and forms the basis for naive Bayesian classification. We will discuss this further on in the worked example. Now if we look at the actual Bayes theorem, it reads, given a hypothesis H and an evidence E, the probability of the hypothesis before getting the evidence and the probability after getting the evidence are related as follows. P of H given E is P of E given H into P of H divided by P of E. P of H is the prior probability of a given hypothesis. So, if we consider our hypothesis to be presence of COVID, an evidence could be presence of fever. So, the presence or absence of COVID P of COVID is equal to yes or P of COVID equal to no are termed as prior probabilities. These probabilities are known by the domain expert beforehand, before studying the features of the incoming patient. We also have what is known as marginal probability represented by, we have just learnt about P of H. We also have a marginal probability P of E. Let us say the presence or absence of fever, or the presence or absence of breathing difficulty. These form the marginal probabilities. Now, P of E given H in this case would be the probability that fever is high or present given that the patient is known to be suffering from COVID. So given the prior and marginal probabilities, we are expected to evaluate P of H given E. P of H given E is, in this case, is the probability for COVID to be present given that an evidence of fever is found. So this is how one would calculate the presence of COVID given an evidence. Just to understand how Bayes' theorem works, let us look at this case of a deck of cards. So you got probability of king. Out of 52 deck of cards, only 4 of them are kings. So the probability of drawing a king card is 1 by 13. If you look at the conditional probability, P of king given face indicates that given that we already know the drawn card to be a face card, what is the probability for the face card to be a king? Now we know that the face cards can either be jockey, king, queen. 3 of them. Okay, so representing P of king given face in the Bayes' theorem equation, you get P of king given face is probability of face given king multiplied by probability of king divided by probability of face. So probability of face, drawing a face card, is out of a total of, you got an ace too, I'm sorry. So out of the 52, ace is not 1. So out of the 13 cards per suit, 3 of them are face cards. This is true for all the 4 suits. So probability of face is 3 by 13. We have already calculated the probability of king to be 1 by 13. P of face given king is, given that a card drawn is known to be king, then its probability of being a face card is 1. So a king card is always a face card too. So substituting these values into the equation, we get P of king given face to be 1 by 3. So this is how we will use the concept of conditional probability to evaluate the Bayes' theorem based equation. Now Bayes' theorem is named after its contributor, Thomas Bayes. Moving ahead, if we look at the Bayes' theorem, if we consider 2 different conditional probabilities, P of A given B is P of A intersection B given P of B. P of B given A is P of B intersection A divided by P of A. Now we know that intersection of 2 events is commutative in nature, hence A intersection B evaluates to be equal to B intersection A. So the numerator in both cases is the same. So in both cases we have P of A intersection B to be, if you consider this equation, P of A given B multiplied by P of B given A, which is also equal to P of B given A multiplied by P of B. So when we move this term to the other side of the equation, equality operator, you get P of A given B is equal to P of B given A multiplied by P of B divided by P of, this is P of A. So this is multiplied by P of A divided by P of B. Please ignore this because this is not the right calculation. So this is how we have come into the Bayes theorem calculation. Now, like I mentioned, P of H here is the probability for a given hypothesis to be true is supposed to be prior probability. So P of H determines how probable the hypothesis was before even observing the evidence. Even before the evidence is seen, the values of P of H for all possible hypotheses must be known. P of E given H, let's look at P of E first. P of E is the marginal probability which measures how probable is the evidence under all possible hypotheses. Whereas P of E given H, which is the likelihood, tells us how probable the evidence is given that we already know the hypothesis to be true. In presence of these three terms, we hope to calculate P of H given E, which determines how probable the hypothesis H is given that we have observed the evidence E. Going ahead. Now let us see how naive Bayesian classification works. If we look at the Bayes theorem in a generic format, suppose there were n hypotheses, which were mutually exclusive in nature, and exhaustive list of hypotheses. So these are the only possible hypotheses, and hence they are termed as exhaustive set of hypotheses. They are also mutually exclusive, so when we pick two different hypotheses, then they cannot be both true at the same time. More than one hypothesis cannot be true at the same time. A given hypothesis being true automatically implies other hypothesis to be false. So that is the meaning. Now when we use Bayes theorem to represent the same, that is, what is the probability for a given hypothesis Hi to be true under the observation of evidence E is given by sigma I is equal to 1 to n for all the hypotheses. P of E given Hi multiplied by P of Hi given divided by P of E. So for all HIs, you can notice that the denominator is going to be common. So P of HI given E is true for that value of I that maximizes this term sigma I equal to 1 to n P of E given HI multiplied by P of HI. I hope I'm clear to you. So whichever I maximizes the value on the right hand side, the same HI is supposed to be true. The remaining HIs are all assumed automatically to be false. Now if we look at this example data set provided here, now this data set this data set provides us the information of 14 days of weather insight. So it takes in the value of outlook, humidity, wind, and tries to identify the final outcome, play. So the class here is play, which takes on two labels, no and yes. At the same time, the non-class attributes or the descriptive attributes here, outlook takes values sunny, overcast and rain, whereas humidity takes values to be high and normal, and wind takes on values to be weak and strong. Now, if we were to construct a classifier, we are supposed to evaluate P of HI, which are the priors or the prior probability, the likelihoods P of E given HIs. So these frequencies together as a bunch form the classification or the naive Bayes classification model. Now the prior probabilities are P of probability for play is equal to yes, probability for play equals no. For the sake of simplicity, I am just going to write it as P of yes and P of no. Now let's look. We have a total of 14 records, D1 through D14. So out of 14 records, let us count how many yeses we got. 1, 2, 3, 4, 5, 6, 7, 8, 9. Out of 14, 9 of them are yeses. And out of these 14, the remaining 5 of them are no's. So these two probabilities constitute the prior probabilities. Now if we look at the evidences, we have evidences in the form of feature values. You got outlook taking on values sunny, overcast and rain. We have humidity taking on values high and normal. Then we also have the attribute wind, which takes on two values, weak and strong. So we need to evaluate the likelihoods for all of them. For instance, probability for outlook equals sunny given play is yes. Similarly, outlook equals sunny again given play is no. For each of play is equal to yes and no. Okay, we need to calculate output P of probability of outlook equal to overcast given play equal to yes. Outlook equal to overcast given play is no. Outlook P of outlook equal to rain given play equal to yes. Probability of outlook equal to rain given play is no. Repeat the same for humidity as well as wind. So the overall classification or the classifier is represented in the form of two sets of tables, one of prior probabilities and likelihood tables of the individual features. We have calculated and represented the same as values here. Let us quickly see how it works. We have already evaluated the prior probabilities. Let us see how it works for outlook. Going back to the data set, let us calculate out of the 9 yeses, that means with a denominator of 9, how many of them have outlook equal to sunny? So this is a yes but with an overcast, yes but with a rain, yes but with a rain, a yes but with an overcast, yes is sunny. 1. This yes is also outlook equal to sunny. 2. So outlook equal to sunny will take on a value of 2. Similarly, we need to calculate the other values as well. If you consider outlook equal to probability of outlook being sunny given play is no, then we have a total of 5 play to be no. Of these 5 play equal to no, we must evaluate how many of them have actually outlook equal to sunny. So the first record D1 is sunny, second is sunny as well, this is not sunny, this is sunny as well, that is 3 out of 5, and this is not sunny, so this is 3 out of 5. Okay. So this is how we calculate the likelihood values. Okay. So outlook being sunny, for play is equal to yes is 2 by 9 as we calculated. Outlook equal to sunny given play equal to no is 3 by 5. Outlook equal to overcast given play equal to yes is 4 by 9. Outlook equal to overcast given play equal to no is 0 by 5, and so on. So this is how the likelihood tables are calculated. So all the tables towards the left side of the screen form the naive Bayesian classifier for the data set provided. Now let us try to evaluate for a sunny day. So the new instance that is given to us is outlook equals sunny. Now we must evaluate H. H1 is P of play equal to yes. H2 is probability for play equal to no. We need to evaluate P of hi given E for each of I equal to 1 and I equal to 2, which I have done here. P of yes given Sunny is P of Sunny given yes multiplied by P of yes divided by P of Sunny. So let us calculate the value of probability of Sunny given yes. So probability of Sunny given yes. Okay, so wherever the arrows meet is where you get the numerator, that is 2 out of 9 records. 9. Probability of yes is 9 by 14. It's given here. Probability of Sunny, go for the row total 5 by total number of records 14. That would be the denominator. So when we calculate, you get 0.4. Similarly, you would calculate P of H2 given E, that is P of play equal to no, given outlook equal to Sunny, which evaluates to 0.6. So when we look at these two values, you can easily notice that P of no given Sunny has a bigger value, and hence the prediction is play equal to no. So for this one, the actual prediction is play equals no based on the data set given and the naive Bayesian classifier. So this is how one would calculate the predicted value or the predicted class label with a single feature value. Now what if we have a situation where a string of features and their values are provided, and we are asked to predict the class label. Let us look at another scenario here. So we are given outlook equal to rain, humidity is high, wind is weak. We are supposed to predict the class label whether play is equal to yes or no. So representing the same in terms of naive Bayesian classification, we have probability of play equal to yes given outlook is rainy, humidity is high and wind is weak. Now here we will take the advantage of conditional independence or class conditional independence. Conditional independence says that for a given class label, in this instance, for a given class label play is equal to yes, all these 3 features are independent of each other. In probability, when we have the 3 features that are independent of each other, then they could easily be considered as multiplication operations. So we have probability of play equal to yes given outlook equal to rain multiplied by probability of play equal to yes given humidity is equal to high, probability of probability of outlook equal to rain given yes, probability of humidity is equal to high given yes, multiplied by probability of wind equal to weak given yes, and finally multiplied by P of S, which is your H. So we have simplified P of E given H. Now we actually had P of E1 intersection E2 intersection E3 given H, and we said all these E1, E2, E3 are independent of each other for a given value of H. We are reducing them to be P of E1 given H multiplied by P of E2 given H multiplied by P of E3 given H. This is what the right side of the Bayes theorem, numerator of the Bayes theorem is. Of course, we need to finally multiply the result with the prior probability. So, let us look up the likelihood tables to calculate these, to find these values. Probability of outlook equal to rain given yes. So, probability of outlook equal to rain given yes. So, that is 3 by 9, excuse me. 3 by 9 it is. Probability of humidity equal to high given yes. Go back. Probability of humidity is equal to high given yes. Given yes. So that is 3 by 9 again. Coming back, this is 3 by 9 as well. The next term is probability of wind equal to weak given yes. Probability of wind is equal to weak given yes. The value is 3 by 9 again, representing the same here, multiplied by probability of yes. So probability of yes is 9 by 14. So multiplying the result by 9 by 14, we end up with the value 1 by 52. And it evaluates to around 0.0714. Similarly, we calculate the other P of Hi given E, and it evaluates to 0.0132. Out of the two possibilities, we have P of yes given the evidence to return a higher value. So because P of Hi given E is argmax I of P of E given Hi into P of Hi, we have the predicted value to be yes. So the play here will be yes. Okay. So this is how we solve the situations where multiple feature values which may not have been already present in the data set be given, and we use the tables of naive Bayesian classifier to actually predict the outcome of the hypothesis. As I mentioned, learning will be actually populating the prior probability as well as likelihood tables. The actual classification works in this manner. Now, naive Bayesian classification has found extensive use in spam email filtering, news classification, medical diagnosis, and weather prediction. The worked example we have taken in this instance is a simplified case of weather prediction. So I was saying that naive Bayesian classification has all these advantages, finds applications in all these domains along with many others. Now, naive Bayesian classification does have its own set of advantages and disadvantages. The first advantage being naive Bayesian classification is very fast to train. That means irrespective of the size of the data set, you just need a single pass through the entire data set. So a single scan will result in the naive Bayesian classification. Just as it is fast to train, it is equally fast to classify. So classification only means you need to look up the classifier model. That means the table of prior probability probabilities and the list of likelihood probabilities. So it is equally fast to classify. Another advantage of naive Bayesian classification is it is not sensitive to irrelevant features. So we have set of evidences in the form of features influencing the actual class label given by H. So E1 influences H, E2 influences H. So for an irrelevant feature, let us say E2, that doesn't influence H as much, let us suppose. So what we do is when we evaluate P of H given E, then it is P of E1 given H multiplied by P of E2 given H, followed at last multiplied by P of H. Fact. Whatever. So, whenever an irrelevant attribute E2 doesn't have enough effect on the hypothesis H, then the effect P of E2 given H is reduced. Thereby, that evidence actually weakens probability of P of H given E. Yet another advantage of naive Bayesian classification is it works equally well on discrete as well as real valued features or attributes. One more thing to note is naive Bayesian classification handles streaming data very well. Data whose attribute values keep changing very quickly is also handled well by naive Bayesian classification. Now, naive Bayesian classification is mainly plagued by one disadvantage, is that it assumes independence of features. So, in cases where features are related to each other, then there is possibility for naive Bayesian classification to fail. Let us take this example for instance. We have a data set which takes in the gender of a person, the number of pregnancies the person has had, presence of blood pressure, identification of breathing difficulty, and finally, if a person has COVID. So this is the data set one has collected. Let's suppose presence or absence of COVID is your class, and these are all our descriptive attributes. Now, for presence or absence of COVID, all the features are supposed to be independent of each other. That means, for a patient who has come suffering with COVID, the value of gender is independent of number of pregnancies, which is not true in the real case. For gender equal to female, number of pregnancies can be 0 or more. For gender equal to male, the number of pregnancies is always 0. So in that case, there is dependence of features between gender and pregnancy. So in that case, naive Bayesian classification might fail. That is because gender and pregnancy are supposed to be, number of pregnancies are supposed to be two different bubbles floating in the air, and there is no correlation between them. In the next step, we will discuss about Bayesian networks which address this drawback of naive Bayesian classification. They acknowledge the dependence among features. So gender equal to female, as a forbearance on number of frequencies and so on. So that we will discuss in the next video. Thank you everyone for watching this video.